Welcome to The Explainer. Today we're looking at the ghost in the disk, how inodes limit disk capacity. It's a classic infrastructure mystery that has haunted, well, pretty much every system administrator at some point. A crashed server that's screaming, disk full, even when the storage numbers say otherwise. Let's uncover exactly why that happens.
Okay, let's dive into this. Picture the scene. It's 2 a.m. Out of nowhere, the core logging application for your infrastructure completely crashes. By 2:05, your monitoring alerts panel is just flashing bright red. It's a critical situation. So by 2:10 a.m., you're logged into the terminal, rubbing the sleep out of your eyes, dealing with that familiar 2 a.m. adrenaline spike, and you are ready to troubleshoot a live production outage.
You pull up the logs and there it is, the unmistakable, fatal terminal error message. No space left on device. It's a hard error. Just to test it, you try to run a simple touch test.txt command just to create a tiny 1-byte file on the directory. But no way. The terminal throws that exact same error right back in your face. The system is completely locked out from writing new data. So naturally, you do what anyone would do, right? You check the disk space usage across your logical volumes using the standard df-h command. And the output, well, it kind of makes you blink and look twice. The var directory is only sitting at 54% block capacity. You look a little closer and the system shows that there are actually 23 gigabytes of raw block storage completely free on the solid-state drive array.
So here's the ultimate paradox. On one hand, the operating system is throwing a brick wall at you, saying no space left on device. But on the other hand, the hardware reality is that you have 23 gigabytes of free raw block storage. The hardware is absolutely fine. It literally feels like you're looking at a ghost. Why is the OS seemingly lying to us? Well, the truth is, the OS isn't lying at all. We're just looking at the wrong metric. To solve this mystery, we've got to understand the hidden architecture of the Linux file system. See, we haven't actually run out of storage space, we run out of inodes. So what exactly is an inode? Well, an index node, or inode, is a unique metadata entry. In the Linux world, a file isn't just a collection of storage blocks. Every single file, directory, or symlink requires this metadata slot to track its ownership, its permissions, and, most importantly, the critical pointer maps that tell the system where the physical blocks actually live on the disk. And this brilliantly illustrates the core concept here. Think of your hard drive like a massive physical warehouse. When you check your standard disk blocks, you're looking at how much physical space inside the building is filled with boxes. But this warehouse also has a person at the door with a clipboard, tracking the location of every single item. Those clipboards, those are your inodes. If that clipboard runs out of blank lines, it honestly doesn't matter if the warehouse is completely empty, you cannot check in a single new item. So your disk capacity is limited not just by physical space, but by the ability to track what's actually in that space. So how does this change our troubleshooting process? We need to shift our diagnostic scope. We started by running df-h to check the hardware block capacity, which completely misled us. Now we're going to append the I flag. We run df-i to check the file indexed allocation limits instead. This one little letter completely changes our view from physical bytes to metadata structures. And boom! The df-i command reveals the true culprit. The I use percentage, that's the inode usage, is sitting at exactly 100%. The server has literally run out of file tracking slots. All 4 million inodes allocated to this partition are entirely consumed. If you create millions of empty or tiny files, you're going to saturate your index allocation map long before you ever fill up the actual hardware blocks. Now the hunt really begins. We obviously have an inode vacuum somewhere on this disk, but standard directory scanners, they'll just hang in a system this dense. We have to get clever with a custom pipeline. We scan exclusively on this file system, pass each directory path to a subcounter to tally the exact files, and then sort the numerical results in reverse order. We essentially want the heaviest folders to bubble right up to the top of our terminal. Our custom pipeline finishes executing, and it prints a pretty shocking discovery. Over 3.5 million files are stacked up in a single directory, /var/log/app/sessions. We hit the nail on the head. We found the culprit. A misconfigured container application was generating thousands of empty session token micrologs every single hour. It completely bypassed the log rotation service. Ironically, because they were essentially empty text files, they took up exactly 0 kilobytes of physical disk space, but they ruthlessly ate almost all 4 million of our available tracking clipboards. Now, here's a really fascinating trap.
We found the bad directory, and the most instinctual thing to do is jump in and type rm-rf star to force delete everything and clear the space. But whatever you do, do not run that command.
Here's exactly why that command is going to backfire on you. When you use the wildcard asterisk, the shell expands that character into an explicit list of every single file name before running the deletion command. You are literally attempting to pass 3.5 million arguments to the remove command all at once. This will instantly throw a fatal argument list too long error, and it'll crash your terminal session memory entirely. You're just stuck. To safely purge millions of microfiles without crashing your environment, you have to stream the deletion cleanly. First, we use the find command, targeting our specific sessions directory. Second, we narrow it down by appending -type F for files and -name star.tmt to ensure we're only targeting those rogue session tokens. And finally, the magic touch. We use the native -delete system call flag. This processes the file system tree sequentially, streaming the delete process directly through kernel space without ever expanding the shell environment argument array. It's an absolute game changer. The command runs cleanly. We check our system parameters one more time with df-i, and man, the relief just washes over us. The inode allocation instantly drops down to a completely healthy 12%. 88% of our index nodes are free again. We run a quick test file creation, and it writes successfully. The application spins back up, the logs start streaming normally, and the production block is perfectly cleared out. We're back online. So the absolutely crucial point here is how this incident fundamentally changes how we view system health. This capacity is a two-dimensional metric, right? It's not just about raw bytes, it's equally about tracking structures. If you're only monitoring raw byte consumption, you're flying totally blind to metadata architecture failures. The actionable takeaway from this explainer is to immediately update your infrastructure team's monitoring templates. You need to trigger critical alerts when either the physical blocks from df-h or the metadata index slots from df-i cross an 80% threshold. We've seen how easily a tiny misconfiguration can silently eat millions of invisible tracking slots while leaving your gigabytes completely untouched. Which leaves us with this final thought. If your system crashes tonight and it claims it's full, is your monitoring blind to metadata? I highly recommend you go check your metrics right now. Keep learning, check both dimensions of your storage, and thanks for exploring this concept with me today.